Okay, cool. So the next question that we have here is, well, we have a little electric circuit full of capacitors, and we got a couple different parts of this question. So the first part is we got to find the equivalent capacitance of all of the capacitors combined, and then the charge stored on all of the capacitors combined on that big equivalent, and then we have to find the potential, which is pretty much saying find the voltage across, or find the voltage and the charges across capacitor C1, C2, C3. So we just got to find those individually, and yeah, that would be all that we need for this. Okay, cool. So let's redraw the circuit so we can like kind of see the process and how we're going to compress all of these capacitors into a single equivalent capacitor. Okay, let me first draw out the rules and how we're going to combine them. Okay, so there are two ways that capacitors can be arranged. They will either be in parallel or in series. Okay, so, and we have to deal with them differently. So parallel capacitors add them up. Okay, so in this case, CEQ is just going to be the sum of all of the C parallels. It's kind of, and you'll see there are some similarities that we have with resistors when we go into series capacitors. These are kind of like parallel resistors. So the equivalent capacitance of series capacitors is going to be the sum of the inverse of all of the series, and then you have to invert it. Okay, so it's pretty much the same procedure that you would follow for parallel resistors. Okay, so this is the strategies. With these two rules, we can compress all of these capacitors into a single equivalent capacitor. Okay, so let's redraw the circuit and get that process started. Okay, so let's start with drawing the voltage source here. Sometimes you'll see voltage sources drawn like this. I feel like that's kind of a dangerous thing to be doing with capacitors because if you don't draw those lines at different lengths, it can be it could be quite confusing, or quite easily to confuse that with a capacitor. So instead, I'd recommend that you always draw your voltage sources like this, so it's impossible to confuse them with capacitors. Okay, but you got to be ready for both. It's just my recommendation is to draw them like this. Okay, so here, as you can see, we got immediately out of this voltage source, we got three branches. So we have a 2 microfarad branch. We also have a 4 that is in series with another 4. And this is C3. Okay, and another branch on this is going to be C2 and 2 microfarads. Okay, and those three branches all come together like this, and then they all lead into the next part of this node is a 3 in parallel with a 3. So this is 3 microfarads in parallel with another 3 microfarads, and this was C1. Okay, so like this, and then those two come together and then go right back to the other end of the original voltage source. Okay, this is exactly the same circuit as you see here. It's just redrawn so that it might be a little bit more clear of who's parallel and who's in series with each other. Okay, so let's draw some colored circles around here so we can kind of see who's in parallel and who's in series with each other. So let's start with a red circle here. I can see that these two are in parallel. I can see that in this green circle, these two are in series. Okay, so let's do a simplification of those parts, and then we'll get even closer, and then we can do the step again. I just don't want this to get too cluttered. Okay, so have no fear about redrawing the same circuit over and over again. It's a lot easier if you have like you know, a drawing tablet where you can copy paste this stuff, but you know, depending on your situation, redrawing it might be necessary. Okay, so let's do in green the CEQ of that. So we know that we got two things that are in series. So we got to follow the series formula, which is going to be 1 over the first capacitor value, which is 4 microfarads, plus another 1 over 4 microfarads, inverse that, and the result of this is going to be 2 microfarads. Anytime you do an operation like this and you have two of the same, it's going to be precisely half. Okay, so sometimes as you get more practice, you'll kind of see these rules or these little shortcuts that you can use. But try this out in your calculator. You'll definitely see that we can. You'll come to 2 microfarads. Okay, now for the red one, well, we just have 2 capacitors in parallel. That's fairly straightforward. We just do 3 microfarads. Plus 3 microfarads again, and with some quick maths, 6 microfarads. Nice and straightforward. Okay, you can kind of see how that works. So we can redraw the circuit with our new capacitor values, and we can get, we're one step closer to having a simplified total capacitance. Okay, so we had the 2 that was here. 2 microfarads. Here we had the green one, EQ. This was also 2 microfarads. Those came together like that. And then the other one was untouched, but this was 2 microfarads, C2. And then those came together towards the branch that we circled in red. So that's going to be the red CEQ. And we combine that into a single capacitor that we found to be 6 microfarads. And this is our next step in our circuit. Okay, so what can we see about this? Let's we could possibly identify this section as a parallel. Parallel capacitors in this section. So let's find the equivalent capacitance of those 3 in parallel. So CEQ. Well, they're in parallel, so we're just going to add them up regularly. So it's going to be 2 microfarads plus the green 2 microfarads, and just so that the colors line up, plus another 2 microfarads. Okay, you can see how all those add up. This is equal to a solid 6 microfarads. Nice and simple. Okay, so to redraw the circuit like one last time, whoops, plus minus, that was 20 volts. 20 volts. We have a 6 microfarads. So I'll do that in blue so that we're consistent with our coloring. 6 microfarads, and then it was attached to the red 6 microfarads. Okay, and as you can see now, we can hopefully very clearly see that this is going to be a series situation. So our CEQ of our whole circuit is going to be 1 over 6 microfarads plus 1 over 6 microfarads, all inverse, and since they're the same, we know that it's just going to be half. So that's going to be 3 microfarads. Okay, so our total circuit total equivalent circuit looks a little something like this. We have a 20 volts in that is attached to 3 microfarads And that's it. So that would address the first part of the question here, which is asking us the equivalent capacitance of all the capacitors, 3 microfarads. Hopefully we have the same answer down here. Part A, 3 microfarads. Yeah. Okay. Don't worry, like this unit, like the 1/4 thing, that's supposed to be micro, like the Greek letter mu, but I guess there's just some technical issues that are not making it appear properly, but have no fear. We can still understand what it means, okay? Now, the next part of the question is asking us, what is the charge stored in the equivalent capacitor? Which is just here. Okay, so the fundamental equation that we want to use to address this situation is this. Q equals CV. Q being the charge, capacitance, voltage. Okay, so if we wanted to sub in, well, look at the numbers that we have here. We have the capacitance right there, the C value. We have our voltage, 20 volts. So this is going to be fairly straightforward. Q is going to be 3 microfarads multiplied by 20 volts. So this is going to be equal to 60 microcoulombs. Keep in mind that the micro from the 3 microfarads is going to be transferred into here. Like if you could easily convert that to a times 10 to the negative 6, and you would come to the same result. Okay, so you can see that here we have 60 microfarads. Yeah. This really means the same thing. Okay, so now that we know that we have 60 microfarads, now we want to find the potential and charges across capacitors 1, 2, and 3. Okay, so we actually want to maybe go in reverse to see the charges, because Q equals CV, that's like the big equation that we want to be focusing on to find all of these charges and voltages across the capacitors. Potential is another way of saying voltage. So a rule that I want to mention first is that all series capacitors, have the same charge. All parallel capacitors have the same voltage or potential. Same way of saying the different things. Okay, so these are the golden rules that we want to follow as we proceed. All series have the same charge, all parallel have the same voltage. And going backwards, knowing that our charge is this and our original voltage, we can quite easily retrace our steps with all of our original circuits and find our way to victory. Cool. So here we know that the charge here is going to be, not 20, it's going to be 60 microfarads. Okay, which means up here they're in series, and we know that all series capacitors need to have the same charge. So here we have Q equals 60 microfarads. Here we also have Q equals 60 microfarads. Okay, so we're going to keep breaking this down, and we know that all of these together had 6 microfarad, 60 microfarads. Okay, the bottom is still Q equals 60 microfarads, and we know on the top all of them together are going to have 60 microfarads, but individually they're not. Okay, so first we need to find the voltage before we can find these. So for here, we know that Q equals CV, which means that Q over C is equal to V. So we want to know the voltage across the blue. So let's call that V blue is equal to 60 microfarads over 6 micro microcoulombs over 6 microfarads coulombs, and this will be VB is equal to 10 volts, which makes sense because we have a 20-volt source. Half of it goes into the first 6 capacitor, and then half of it goes into the second capacitor. Okay, so we know that all of these in blue all have voltage blue, which is equal to 10 volts. Okay, so to find the charge across them is going to be Q equals CV. And all of them have is equal to C, which is 2 microfarads, multiplied by 10 volts. All of them have Q is equal to 20 microfarads. I mean microcoulombs, my bad. Don't make mistakes like that with your units. They are quite delicate and important. Okay, so here we have Q is equal to 20 microcoulombs, and the voltage is 10 volts. Okay, so that would be C2. I'm gonna write this down at the bottom here. C2. Just so we have like all of our answers compiled at the end. In the same place, we had V is equal to 10 volts, and the Q associated with C2, that was equal to 20 microcoulombs. Cool. And so we can keep retracing our steps, and we can see that, okay, we have another parallel situation, and we know that these two both had the V across there. Let's call this VR for V red. This was 10 volts as well. Okay, so given that, we can find C1. So QC1 is equal to C1 over VR. Right? C over V. Q equals CV. My bad. I'm tripping. C1 V R. And we know the voltage across them is 10 volts. And the capacitance is 3 microfarads. Multiplied by 10 volts. It's QC1. This is equal to 30 the microcoulombs. Okay, so we can write that at the bottom as something else of our final answers of interest. C1, we had 30 microcoulombs, and there's also 10 volts. Okay, so that's C1. 10 volts, 30 microcoulombs. Cool. So all that's left here is we got to get the green. That's the last thing, because green contains C3. So we know that the Q of C3 has to be equal to the Q of C2. Right? Wait, my bad. That's not true. That's not true. We know that the voltage of across that whole series is the same as the voltage across C2. So we know that the V green is equal to V green is going to be equal to 10 volts, right? Because it's in a parallel path, and we know that the C2 has 10 volts. So since you know, the entire green has to also have 10 volts. We know that the charge of the entire green is going to be the same. So Q green is also going to be equal to that of C of is going to be equal to QC2. and that's because like they have the exact same value. Yeah. Yeah, so we know that the equivalent capacitance of C green is going to be 2. So to find the charge, we got to do Q equals C green. I'll just say CG times V, which is 10 volts. And we know that that's going to be Q is equal to 2 microfarads times 10 volts. Q is going to be equal to 20 microcoulombs. And we know that all capacitors inside all series capacitors are going to have the same charge on them. So we know that Q, the charge on C3 has to be 20 microcoulombs too. So let's write that down at the bottom. It's 20 microcoulombs, but the V value is going to be different. Okay, so we know here that Q over C is equal to V, and we know that Q is going to be we're looking for the voltage just on C3, right? And we have two things in parallel, in series. Like we have a 4 attached to a 4 in series. So the Q, we just calculated that to be 20 microcoulombs, my bad. I want to divide that by the value of the capacitance of C3, and that's going to be 4 microfarads. And this is going to give us our final voltage, which is just 5 volts. And that actually looks like a very reasonable answer, because we know across this entire capacitor branch in the middle of those two series capacitors is going to be 10 volts. So only one of them, knowing that the two capacitors are identical, one of them should have half the voltage, which is 5 volts. So that makes perfect sense. So this is going to be 5 volts. Okay, and these would be our final answers for finding the potential as well as the charge on capacitors C1, C2, and C3. Okay, so yeah, that's that. So in this situation, it would be very good to keep track or to redraw the circuit many times, because as we're going back up through our process, having those intermediate circuit diagrams was very useful. Okay, so now that we have all of that, we have, yeah, all of these numbers seem to line up. It's just I've been using the prefixes, and here it's using the scientific notation, but it is all going to be the same thing. Cool, so the above solution is good. What happened?